CAD this evening and how important it is. You've heard us talk about it. And some of you are going to know everything I say, and some of you are not. Some of you are going to be totally lost, like Victor. And he will not be. Victor will be like, what's he talking about? I thought I knew how to do this.
I thought we were talking about food noodles tonight.
Laser pointing.
Okay, when I was a kid, when I was your age, I took drafting.
This wasn't enough magic.
This is the kind of thing that I did. So Gary, we named this, it's Gary up there, named the shop after. He also learned drafting. That's what the class was called, drafting. I got an A in drafting. And this is what you did. So this is all done with pencil. You use a device like that on the right. It's a square that's, you can adjust the angle of it, and it's connected to parallel arms, so you can move it all over the table, and it keeps its frame of reference. So to make different lines, you use different hardnesses of pencil, and then your friends are the tools of the trade, which are there. Who knows what that thing is on the lower right?
Lower right.
What is this? But you don't even know what that is.
I see a smiley, frowny face.
There is that. So that's your second best friend. Your best friend is that guy in the lower left. So what's the thing on the lower right? Question?
You said lower right is a stencil.
No, it's not a stencil.
The
Yeah.
triangle, that's a protractor.
So on the lower right, which would be there, what is that? It's very thin metal. What's it used for? It goes along with that. Is that? That's an eraser, isn't it?
Yeah.
It's like a calculator. So it's an eraser shield. So you go and make your drawing, you make a mistake. By using the shield, you could cover the parts you didn't want to erase, and you just erase in the slot, and it cleans out that little bit of a line. So if you made mistakes or you put something in the wrong spot on the drawing, it's like, okay, start over. Do it over. You couldn't, there's no other option. So you had to do a lot more planning. With the CAD program that we have, you don't really have to do any planning at all. These are the tools you use. So a ruler, that's a measuring device, has 2 points on it. You use a compass for making circles, but that one there with 2 points is actually, is that 2 points? That's for measuring. So you can transfer distances from one place to another. So these are in the olden days, and Gary only learned the drafting. He never learned CAD. So when this is the Bat Hawk, by the way. He designed the Bat Hawk. And then when he designed it, he'd sit with Caleb Schlenker, who was Isaiah's brother. And he just walked him through because we had to put it into CAD. So Caleb put it into CAD eventually. So this is a sheet of paper. This is a C size. Let's see. So there's 4 different sizes: A, B, C, and D. A is the regular letter size. So that's mostly what we use here when we print something out, because that's what our printers will handle. But you can get these. You would make this as big as you needed to. Use a bigger size sheet if you needed to make bigger drawings. And then when they copied these, they made what are called, I said, what happens when you copy that? What do you get? A blueprint. You make blueprints out of them. So you make one original and then make a bunch of blueprints. So, and blueprints, they're called blueprints because they actually are blue. It's like a copy system that you use There's like a blue background all over. And then, so you can see he's got a lot of detail in here, much more than you'd ever think of when you looked at that little bat hawk. So CAD, what does that stand for?
Computer-aided design.
Computer-aided design. So that's what we're doing with CAD, we're designing things. Ultimately, we need to make things, but before you make things, you need to design them. We get to use a computer to help us design it. It makes it so much easier. If I wanted to move, if I were in a drawing, I wanted to move something around, because you guys actually, I don't think any of you have used the drawing part of Inventor, but there is a drawing part in there. If you wanted to move something, you just grab it and move it. Everything moves with it, so it's real simple. So we use CAD because it helps in the development. So ultimately, you have to come up with the idea yourself, right? The computer-aided design isn't going to design it for you. You have the tools to do lines, circles, squares, whatever, extrusions, assemblies, but the program isn't going to design it for you. The idea has to come out of your head. This is just a way for you to get it down on paper. When you get it down on paper, that enables you to, how does that help? You get it down on paper. Anybody? Picture?
Visualize it better, so you can like change it. Because if you have something in your head, it's not very precise.
Right, yeah, when you first think of ideas, they're kind of in your mind. When you go to put them down on paper, okay, now, oh, well, that didn't work quite right, or that isn't the right size, or whatever. Why else is the paper helpful?
It allows you to communicate the idea with others.
Communicate with others. Okay, here it is. Take a look at this. This is what I meant when you couldn't understand what I was saying, because you can't see inside my brain. So now I put it on paper, or in our case, in the computer. So that's going to help us explain that to other people. And then we can analyze the idea and talk about it and communicate with others and revise it as we go on while it's still just in the computer. While there is no hardware associated with it at all. We haven't drilled a single hole, we haven't picked up a piece of metal, we haven't welded anything. It's all in the computer, and we can change it as much as we want to, and very easily. So that's when you want to keep. So what we do is we iterate means to make a small change, try it, make a small change, try it, make another change, try it. We can iterate the process, the design process, until we get it to where we think, okay, this is pretty good. Let's go ahead and 3D print it, or let's go ahead and machine a part, or let's go ahead and laser cut it out of cardboard and see if we can get it to work. So that's where it helps us. And this is used in all kinds of areas. You'll see why we talk about catalog, because this, if you understand this picture, you'll understand a lot about the way that we work here. You have to be able to do CAD. You have to be able to get your ideas into the computer in a way that they can be visualized. And in our case, this is, what kind of a drawing is this? It's a sketch, sort of?
2D.
It's 2D. We need two what? 2 dimensions. Okay, this way and this way. There's nothing behind there. That's it. It is so thin, it only has one side. 2D. So you can't really, I can't tip that thing to see what it looks like underneath it. But with our computer program, Inventor, it gives us the 3D model. We start out creating sketches in 2D, but then we go to 3D, and then we can actually rotate it on the screen and see what it looks like from the back side. Turn it sideways, get a side view. When you did drafting the standard way you did a drawing, this isn't quite standard, but you can see these are all different views. Here's one view, there's another view, there's yet another view, and there's actually 2 different parts here. So if you turn the piece one way, you can see. And what you try to do in the drawing, you try to get enough views so that there's no more mystery. If you know how to read the drawing, you can figure out what the physical object actually looks like. In the 3D world, it's much easier because you can literally twiddle the thing any way you want to. You can go inside of it. There's all kinds of things you can do to help you better visualize it. But we use CAD as the start for all of our processes. So even if we want to like print out a drawing, so we can explain this or show it to, or email it or send it to someone else and show them the idea. So if we want to print it like that thing on the top there. So you go into CAD, you create your part, and then you create a drawing and you print it. And you might use some things you can print actual size. Why is it helpful to print actual size?
Just so the person who you send it to or show knows almost what it feels like in your hand, you can say.
Okay, what other reasons, Weston?
So you don't have to scale it up or down?
That's right. You can actually use the printout as a template, lay it right on there and mark it. You can mark all your whole layouts, for instance, just right with a full-scale drawing. Now, some things, obviously, the robots are too big to do full size, right? So most of your drawings will be scaled, but it is possible to print full size. And in that case, much like they do with ice carving, with ice carving, they start with a silhouette on paper of what they're doing. So, you know, and it's actual full size. And they take that piece of newspaper and they stick it on the ice. And they take a chainsaw and they cut the profile all the way around the outside. Now they got the shape of it, but it's still all flat in the front. Now they got to go in and get the 3D part of it. So what we're doing here is you're actually taking a full-size template in this illustration we're talking about reprinted, and you actually tape it down to the metal or down to the cardboard or whatever if we're doing a prototype. We're actually going to put it right on there. We're going to mark all the holes. You can also do it, you know, if it's scaled, then it takes a lot longer to do your layout that way. Layout all the holes. So if we can do it full-time, we would, or full size. So then we do a lot of 3D printing over here. We start with CAD again, and we run it through what's called a slicer, and you'll learn the name of the different slicers. We use several different slicers depending on the 3D printer that it's for. And the slicer figures out, Roman, tell us what a slicer does.
It takes your part, and you can change how dense the part ends up being, and then you hit a button called slice. That then creates a G-code program that the 3D printer can actually read, because it can't just look at the object and be like, oh hey, I know exactly how to print that. So it tells it a coordinate system that needs to go to and how much it needs to extrude filament. That then goes into the printer and then you can print.
So why it's called a slicer is because it's as if it takes your part and slices it, like a bread slicer. Really thin, like 0.4 of a millimeter thin. Goes through the whole part and slices it that way. And then it takes that sliced layer and it knows where to run the thing that's squeezing out the toothpaste all the way around. So it'll do that just on that one layer. And it'll do everything on that one layer. Oh, he's counting. Do everything on that one layer, then the table will move like 0.5 millimeter or whatever your layer thickness is. And then it goes and gets the next slice that the slicer figured out. And it does the squeezing of the hot plastic everywhere all the way around. Then it moves it up. So that's why it takes so long. It's got to do everything on one layer at one time. You can't do, it doesn't print uphills, right? It only prints a layer, done. A layer, done. And it either moves the table up as it goes, or it moves the head down. It just depends what printer it is. Roman's got one that prints really fast. So again, we start with CAD, and we run it through a slicer. What's the name of the slicer we use? Cura, C-U-R-A. So we have these programs installed on the same computers that we have the Inventor software on. So if we're going to do a laser cut part, down here we have two laser cutters. One is an 80 watt, it says it's 100 watt, but it only has an 80 watt tube in it. And the other is a 40 watt. The 40 watt one we're really only doing engraving on. So the higher power one, the 80, we can actually cut through a lot of things. So we'll cut through cardboard or acrylic or plywood and build a lot of our prototypes that way. But you have to start with CAD, and then you run it through a program. You actually export from CAD a certain type of file. It's called a DXF. It's the kind of file that the laser printer expects. And then you run it through the program that actually drives the laser cutter. And that is called, what was that?
Lightburn.
Lightburn, or that's one of them. We use two.
Would be RDWorks.
RDWorks. So, and those are on the computer that's right over by the laser cutter. You can either use Lightburn or RDWorks. Now you don't necessarily, if you're doing engraving particularly, you may not start with CAD, you may start with something like Inkscape or Corel or something like that. But you can, this is a typical path that we use for designing the kind of parts that when we build them in as a prototype. Now if we're going to either the CNC, which is in the far corner over there, that plays the national anthem, or the router, that is a bigger table CNC, but not quite as strong. It doesn't have the... So what gives a router its strength is that C shape, right? There's a table down here, and there's a big, goes back, then it goes up with a big thing, and it goes over and holds the head, holds the spindle, and the spindle spins. So the strength of this C is what makes it so that you can cut steel with it. It's really strong. Now the router that we have, which is over there, just this side of the mill, it has a bigger table, but it's not quite as strong. We can cut aluminum on it. You wouldn't ever cut steel on it. So it's just, it doesn't have the rigidity. And if you want to see something that's really rigid, you go in the third building over there and look at that big drill press on the opposite wall. It has an 1/8" drill in it right now that's that long, and it has about a 4-foot throat. Throat means from the center of the drill point to the back of where the arm is, so that's how deep a piece you can put in there. So it has a really deep throat. And then it comes up around it. That thing weighs tons and tons. So to get to either one of those machines, we use what's called CAM. And CAM is like a slicer. It does the function of a slicer for a 3D printer. But you select your tool for each feature. You select the speed you want it to run at, the speed that it spins at. You select the feed rate that you want it to go. And then you go to the next part. So in each one of these, you'll see there's like, on the left-hand side, once we get into it, you see there's like a browser view there. You can see all the operations, and each one uses a different tool. Each one may have a different starting point. They may run at different speeds. A lot of times, if you're doing different features, like if you're drilling and doing pockets, and doing the outside and cutting something out, they use different tools. So you use a drill and a hand mill and maybe several different things. So before you start those operations, you have to get all those tools set up. So the CAM is what helps you do that. The CAM we use is called Inventor CAM. It's actually built into Inventor. It's a tab in Inventor. And then if you're going to do some in the water jet, which is right back in this room back here, it also has its own program, but you're starting with CAD. So what is the program called?
WAM.
WAM?
W-A-M.
W-A-M. So you have to export from CAD. What kind of files does it take?
It takes DXF or image files known as SVGs.
Okay. So then you run it through that, and that's a cloud-based program.
Yes.
You run it through that program, and it downloads a file, and then you plug it into an SD card in the water jet, and then it knows what to do. Now the water jet is a little different than like the CNC, for instance. The water jet is more like a laser cutter. So it actually cuts all the way through. It cuts all the way through the part. So we don't do any profiling with a water jet. We're just going to cut the outline like we did with the chainsaw on the ice. So you can see that the CAD, knowing CAD, is really pretty essential to what we're doing. So the advantages of CAD, we talked about a few of these. It's very accurate. So it has the visualization. It can be as good as you want it to be because you can zoom in to the smallest, zoom in on screw threads if you want to look at it. So the visualization is amazing. And you can, you know, any place you can send that file, someone else could look at it. It allows for rapid revisions because it's not this paper model that we were forced to use that before. By the way, when things were drawn like this, you'd have whole factory floors full of drafting tables. And all these guys in shirts and ties would be drafting on these tables because everything has to be drawn first. Helps us with collaboration, gives us documentation later. We can go back and say, okay, that gear's inside, I forget what size that is. So we can go to the CAD. So we typically build our full robot in CAD so we can go back and find out what the real thing is. And then, we haven't done much of this, but there are different kinds of CAD. There's an electrical module, so if you were going to do a circuit diagram, you could, there's a plug-in for that. There's architecture, civil engineering, they all use CAD all the time. Even plumbers use CAD.
You also have stress tests and some other analyses.
Analysis, right. Okay, here's the things we're going to talk about tonight. Projects, parts, drawings, and assemblies. Projects is the part that all of you skip. You just get in there and start making a part. So that is not the way to do it. The first thing you have to do is you have to set up your project. In other words, where are my files going to be? So that when I go to look for them next time, they're going to be there. So you typically set up a special directory just for whatever you're doing. Like we will have a directory and our files are on a server, which is, where's that server? Somewhere, oh, it's in the safe. It's in the safe. And it's called TrueNAS, T-R-U-N-A-S. And there's a file folder on there called GrabCAD. And that's kind of an artifact because we used to actually use a product called GrabCAD. We don't anymore. And then underneath that GrabCAD, there are build seasons. 2020 build season, 2021 build season. So we'll have one this year. I think it's already out there called Build Season 2024. So we know that we're going to be in that folder. But you may want to be more specific than that. You may be working on the drivetrain, or you may be working on an intake, or you may be working on a wheel design, or a special manipulator, or swerve drives. So under that 2024, we're going to further refine that by having directories so things are easier to find, because there are hundreds and hundreds of parts we're going to design, and you want to be able to find them. So the first thing you do when you go into let's see. Okay, here's the inventor. The first thing you do, and it depends what the year is. This is 2023. In 2023, the first thing you go to File, Manage, Projects. Before, there used to be a Projects tab on the Home tab in 2022 and beforehand, but now you go to File, Manage, Projects. Now you can see there are a number of projects here, and one of them has a check mark in front of it. The one that has a check mark in front of it, that's the one that's selected. That's where I'm working now. Now, in other words, that's the directory that all my files are going to go into. And when I go to open something up, it's going to look there. When I go to save something, it's going to put it there. So if you start, for instance, if you're working on some part, and you've got that part already in your tray or whatever, you are in a project. It is set to something. And if you start working on a part in another area, and it's going to tell you right away, that is not in this project. It's going to tell you if you try to go to a different directory. And you cannot change projects without closing all your parts. So you can only work on one project at a time. You can work over there, but just realize I'm not where I belong. So when I save this, it's going to go to the wrong place. Sometimes you go to another directory to get a part and bring it in. And that will be outside the project. The first thing to do, without exception, is to set the project that you're working on. It's jumping in, okay, project. So that's the location. So you notice that there's only one TrueNAS. There's only one GrabCAD folder there, and then there's all these other folders. So no matter where you're working in the building, you're all working out of that same file. So if Victor makes a part, it's going to be in that directory. When I go to look for that part, it's going to be in that directory. There's not going to be 2 or 3 of those different parts. We're all working out of the same part. What that means is, it's possible because we don't have a locked revision system for 2 people to get the same part and be working on it at the same time. So don't do that because somebody's going to lose their revisions as soon as you write over it. So some systems protect you from that, like what do the programmers use? GitHub protects it from that. Okay, the next thing we do is we make parts. So we don't start making assemblies, we start by making parts. So all of our robot is made up of parts. It's screws, it's plates, it's bearings, it's gears, it's motors, it's wires, all kinds of parts. And we can either make the parts, or sometimes you can go to a vendor site and they will actually have the CAD already made. It's really nice for some transmission or something. So you just download that and then you bring it in, you open it, you can open that part. Now when you do that, it's usually in a step file, STEP, that's the extension, STEP file. When you do it, and when you bring an assembly in a step file, it is not constrained. We're going to talk about constraints later. So you need to constrain it right away before it blows up on you. Because if you start moving parts of it, it'll just come apart. So it's nice if things are, if it was created in Inventor and you have an IPT part or an ASM part, it's going to work fine. But if it's created in SolidWorks or some other program, you bring it in, but it is not going to behave well until you do a few things. Now we'll talk about constraints because they're very important. So we are sketching and we're basically going in and we are creating a 2D sketch. So let's go back into I'd like to jump around right here. Okay, so we are so I got my part selected. That's my project. So this is just something I opened up now. This is the user interface. And right now, what is that I'm looking at? That's a drawing. So you see it looks similar to this. So we've kept a lot of the forms for the drawing. It's got a frame around it. It's got locators on the sides. It's got a title block that tells who made it, when, what the materials were, what revisions were done. All of that is in the same drawing. We've kept all those same standards. Now, most of you have not seen that, but when you go to right up here in the corner where I am, and you click on that, there are 4 things that you can create, just kind of by default. Drawing is one of them. So you haven't done that very much. So what we're going to do is we're going to go to part. We're going to create a new part. And when I go to create a part, I'm going to start a sketch over here, and I'm going to start a 2D sketch. There is such thing as a 3D sketch.
Why would we do drawings now that we have 3D things? Like, what's the point of doing that?
Well, it's kind of hard to create something in 3D. It is possible to do some things in 3D, like lofts and curves and spheres, but generally you need to start with a...
You mean like the actual?
Like the whole thing. Like the part.
What's your question?
When you're starting a new file, you start with drawing.
No, you don't start drawing, you start with part.
No, but why would you ever do a drawing?
Why would you ever do a drawing? We talked about that. Were you listening? Why do you do a drawing?
Because it's hard to do things in 3D.
No?
So it's when you have to share your project with other people, you're able to print it out and actually show everybody.
Right.
You can't print a 3D object.
Yeah, you don't always have access to a computer, so you may not be able to show them the actual 3D thing. So drawing, you could take it in a group, you could lay it out on the table and say, this is an idea, what do you think about it? Yeah, so drawings are still useful. We don't use them too much, but because normally we have access to a computer, but we do use it sometimes. You notice if I just leave the arrow sitting on something, it's going to come up and tell me what it's about. So it has hints if you don't know what you're doing. So we're going to start a sketch. So I'm going to click here. Now up comes this weird looking thing. This looks like a game, doesn't it? So what is that?
It's planes.
Planes. Okay, it's 3 different planes. So 3D means we're going X, Y, Z. So we have planes in all of those areas. And each one of those planes has 2, so it'll be in 2 directions. It'll be XY, XZ, YZ. Rustin?
Why aren't the planes stretching infinitely long? Or to the edge of the screen?
It would be hard to tell what they were if it did that. They actually do. They actually do.
Well,
you
yeah, I
can
was
use
just
them
wondering.
infinitely, but this is to help you see it better.
I don't know why I thought they would do that. I guess that
Yeah,
would
you can actually sketch on those planes way out. So they are, in fact, infinitely big. But we're going to pick, it wants me to pick one of those planes to sketch on. So depending on what I'm going to do, I may pick a certain plane. And all I have to do is, see they light up as I go over them? And it tells what the plane is. There's the YZ plane. I'm going to pick that plane. And now what it does is, it flips around so I'm looking straight down at that plane. It was magic, wasn't it? I mean, you didn't even see that, so magic. So we are looking straight at that plane, so we can't see the plane anymore because we're looking right at it. So we're looking at a flat piece of paper. And now we have all these options up on top. Now you see all these options up here? Now if I go to this little thing right here, you see where this is? Turn that light on over there somewhere. This little thing right here. If I click on that, it will change my ribbon appearance. That's called a ribbon. This is the ribbon that I like to work with. But every time you click on it, it's going to cycle through ribbons. Whoops, it's this one. See the ribbon's different? The ribbon's gone. There it is again. Now, the reason you might not need the ribbon is because most things are available with the right click in Inventor. That's to help you to work faster. If you aren't using it every day and using all these features, here you can just see what they are and it says what they are. But you can also right click to get most of these. So here it's, when we start to draw, we can draw a line. So let's just, I'm going to click on that. Now you can see that's active. And I'm just going to draw a line here. And to finish it, I'm going to click again. And then I'm going to hit escape. I could also right click and click OK. But usually I use the escape key. So now I'm out of that. Now, what about that line? What can you tell me about that line? Roman?
It's undefined.
It's undefined. What do you mean? It's a line.
It's not defined to any object or origin, and it is not defined in length.
Defined is not the right word.
It doesn't have dimensions or constraints.
Doesn't have, or constraint, dimensions or constraints, that's right. It doesn't have dimensions or constraints. So if I go in there, and this is where you're going to run into problems if you don't constrain your parts. I'm going to grab this line. Let's see, move. Look at that. What if I grab the end of it? Oh look, I can move that. So I've changed everything. How long is that line? I don't even know. So that line is like almost totally useless. I need to constrain that line. And when the line is fully constrained, it will turn white. So what do I need to do to constrain that? Roman said one of them. How about dimension?
What angle is that?
Okay, that's another thing. So let's do the dimension. Let's do the length first. I'm going to click on the line and drag it. And you notice it does this kind of weird, it's not showing me the length of the line, it's showing me how high it is. What if I want to know the length of the line? Right click to the rescue. Align. See that? And now my dimension is going the same way the line is. Did you know that, Sammy? Okay.
I struggled with that a lot, so that's
Okay.
really nice.
So we got that. Now we got a dimension on it, and I could have changed it. I just left it what it was. But look, I can still drag that line around. Kind of escape. Yeah, I can still drag that line. If I go to the end and grab a point, I can still tip it. So it's not constrained. What else do I need to do? What did you say, Sammy, before?
The angle.
Okay, dimension. So what I'm going to do is, to do an angle, I have to do an angle in relation to something. So I can either do the X or the Y axis. So if I go over here on the left-hand side, you see this where it says origin? When you click on that plus sign, you see the 3 planes and you see the 3 axes. So I can make those visible in my drawing if it'll help me. So let's just go over these. Let's see. I don't want that one. I want that one. That's the one I want. I'm going to right click and I'm going to say visibility. See, it's not checked. I'm going to check that. And now that line right there is visible in this drawing. It's not part of the drawing. It's a reference. But if I'm going to set up the angle of this line, I need some line that is not going to change in relation to it. So now I'll go to dimension. I'll click on the line and I'll click on the reference line. And now it's going to come up with an angle. So I'm just going to type in 45. So now the angle of that line, even though I can still move it around, that angle will never change. It is constrained. But you notice it's still not white. Why? What else needs to be constrained?
Whenever you do it, but you need to make it so that way it can't be moved.
What's that?
So you need to make it so that way it can't be moved.
How do you make it so it can't be moved? Roman?
Constraints. So you could do, for instance, perpendicular, parallel.
Well, I can't do perpendicular or parallel. Neither of those will work. It's 45 degrees.
Oh, I guess that's true.
Can't do those.
But you could have a separate line.
I could do a separate line, but I don't want it to move. Weston?
Is there a tool just to lock its X and Y position?
There actually is the tool to lock it, but that does not really help most of the time. It would lock it, but you wouldn't know anything about it.
Define a position.
The position. Okay, so let's do a position. We're going to use a dimension again, and I'm going to take this end. See that? I'm just taking the point. I'm clicking on it, and I'm clicking on the origin, which is right in the center. You see that? Now, I just got a dimension for that. And I'm going to make that, I'm going to make it 1 inch. So it is now 1 inch from the vertical side. Now that line is still purple. So it isn't constrained in relation to this. So I'm going to do it again. Dimension is still highlighted. You see that? Still got a square around it. Click there. And I'm going to click here. And now I've got a height. And I'm going to make that 0.5. My line just turned white. What that means is, I just hit escape. I'm not in dimension anymore. I'm trying to grab that line and move it. I can't move it. That line is fully constrained. And that's what all of your parts need to be. They need to be fully constrained. If you don't constrain them as you're going along, you're going to end up with a mess because you're going to move something or you'll change a dimension and your rectangle will become a trapezoid all of a sudden. And when you get far in, you can sometimes get errors that you don't know what they are. It's because you hadn't fully constrained it. Now, all of your constraint tools are visible right up here. This whole thing is constrained. There's the lock one, so you could just lock it in place. And sometimes when you start with the drawing, you want to start with like a point in a certain spot, and you may just want to lock it there. So I don't want that point ever to move. You can do that. This one is concentric circles. It's a lot. They look like what they are. This is collinear lines. You know what that means? Lines that are in line with one another. They can be different distance apart, but they're in the same line. This one is, what is that? It is, oh look, the hint popped up. Look at that. Isn't that cool?
It's, if you needed an extra constraint, it'll just automatically add it to it. So if it doesn't say fully constrained on the bottom,
Okay.
you can click that and it'll automatically.
Well, look at that, that's it. Okay. This one is parallel, so sometimes you're doing lines, several of them, or you're doing one across the page, you want it to be parallel to that one. You can set that up like if you're building a chassis, you want this part to be parallel to that part, or that line to be parallel to that line. You can also do, this is horizontal, this is vertical. What is this, do you think? Perpendicular, right. What is this?
Tangent.
Tangent, right. So all these, because it popped up, right? So all these things are available, in fact. What does that say? Okay. Anyway, you get the idea for constraints. So if you're going to make something, start constraining it. If your lines aren't white, it used to yell at you all the time if you weren't fully constrained when you tried to get out of it. But it doesn't anymore.
So Mike, I have a question. So when you're constraining something, is it, I'm trying to summarize what you just said in my mind. Does it have to be at least 3 different ways constrained, or is it, if there's not, it could be constrained with 1 or 2, or does it have to be 3 different like angles or shapes?
It
You see what I'm saying? Like,
It depends what it is.
oh, okay.
So in this case, we had to constrain, we had to do the length, we had to do the angle, and we had to do the position.
Okay, because it was a line.
Yeah, because it was line.
Right.
Now if it were a circle,
Right.
you could constrain the center of that circle, and you could constrain the size of it, and
Then it would be done.
that'd be it. So it just depends what it is. Now when you do and there are defaults about what constraints are set up when you create a part, and we'll get into that later. We may never get into it. But there are settings you can set. So you just got to kind of figure out what you're doing when you're. Now if I were a tailor, I would have 2 screens and I wouldn't be going back and forth on them. But we have to go through this and see what we're doing here. Okay. Okay, let's talk about the browser. We talked about the right click. And then we talk about iPhone. So let's go back into here. So this is the model, it's called the model browser on the left-hand side. Now, right now, we've only got one sketch. There's hardly anything else there. Now, if I were to add things onto this, other operations, for instance, this sketch, if I try and close down Inventor now, it won't let me. Why not?
You just saved it.
Because I haven't saved the part. So what you have to do is you have to go here and say Finish Sketch. So I'm going to Finish Sketch. So now that sketch, and it reverted to a isometric view. So that's the way the home view is set up. Now that sketch, you can see that sketch is out here. Here it is right here. Now if I want to go in and edit it again, I can either right click, and there's all kinds of things I can do, like edit sketch, I can delete it, I can make it invisible, I can make the dimensions visible or invisible, things I can do to it. So if I want to go back into it, there I'm back into it. So typically, if I go to save this now, it's going to yell at me. So here's the save. You can't save it when you're editing it, so you have to get out of it to save it. So if you get out of there, finish, and you just need to do this once in a while. You just need to save it once in a while. So now it's asking me where I want to save it. I'm in my 2023 folder, and this is, and it comes up with these default names, part 1, part 2, part 3. Usually you want to name your parts, and giving them identifying names so you know what they are. So when you go to look for it later, you can find it. Because assembly 1, assembly 2 doesn't help. And part 1, part 2, part 3 does not help. However, I'm going to call this part 2. Just to show you that I can. So this browser, especially when you get into assemblies, that becomes quite large. And every one of the, so in an assembly is a bunch of parts connected together or in the same drawing. So if I were in an assembly, I'd see all those parts there. And I could actually go into those and go into the sketch for each one. Now we've done, let's go back into this and go just a little bit further. I'm going to make something that I could, hey, let me try something. Let's see if I can do it. I can do that. You can extrude a line. I thought you could do that. So now I typically, there are a couple ways to look at this. I've extruded it, which means I've taken that point-to-point thing, sketch, and I've extruded it. I said, go ahead and extrude it up. So it's going to extrude it in the other plane. You remember we were looking down on it? When we clicked our plane, we opened the sketch, we were looking straight down on it. When it extruded, it's going to extrude it right up toward you. So that's the way it's going to go. And when in the extrusion box, so let's go back into here. Here's the extrusion. Here's the extrusion. I'm going to go back in here and edit feature. So this box has the direction that it's going to extrude. It could extrude both directions if you wanted it to. Here's how far it's going to extrude. And you can also do other things like, we'll do that here, so there's nothing over here. So we've extruded that plane. So now, it doesn't look like much of a plane, we're kind of looking weirdly at it, but this panel on the right-hand side has this world over here, gyroscope. If I click on that, this circle appears in the middle. Now this is my navigation globe. So notice what happens to the cursor as I move it. Round, flat. So if I come in here, or free spin, this is free spin. So I can spin this thing any way I want to. Just as I move that around, it's going to jockey that around. Now if I come out here, I can rotate it. That way it's going to rotate around the point. And if I go here, it's going to rotate it the other way. So the opposite plane. So when you go in to do that, you need to pay attention to what you're doing. And if you get lost, this little box up here will save you. So it's got a home button. So that's going to take me right back to where I started from. I can look at the top of it, or I can flip it and look at the other side, or look at the other side, or I can rotate it. This little box up here is like a navigation box, so you can use that to change your view on the part. Now let's get a isometric view. Whoops, almost not isometric on this one. There's kind of an isometric view. You notice this box has corners, and it has edges, and it has flat spots. So you can do a lot with that little thing. So now let's see if we can extrude that sheet. So that's essentially a sheet with no with length and width, but no thickness. There's no thickness right now. So now we're going to extrude that sheet. I lied, I did. I'm not sure if I can do this one.
You have to do a sketch first.
Okay. All right, so let's say I'm making something really weird. I mean, you don't usually make things with no thickness, but what I'm going to do is I've now highlighted this. If I right-click on this, I can create another sketch on this. So here we go. I right-click, new sketch. See the things that are available on the right-click up there? A lot of times, the only things that you can do are available on the right-click. It doesn't bring up irrelevant things. Now, not everything is there, but so I'm going to create a new sketch right on top of that sketch. So now we're looking straight down on it again. It's flat. I'm going to create a circle on there. There's a circle, and I'm going to get out of here. Now, what didn't I do? I didn't constrain it. So that circle, it can get all lumpy later. And you never know what it's going to do. So now I can go to extrude, and I'm going to extrude that part. Now I can go that way, or that way, or both ways.
What is the last one, right?
It's two directional, so you can extrude a little bit one way or a lot more.
And you can choose how much you want to go in each direction.
This one?
Yeah.
Which is kind of handy if you don't want to make a whole offset plane. You can just drag it up off the plane entirely.
I didn't know you could do that. Look at that. How cool.
Like, how many times have you used this?
I've never needed that.
I use it all the time.
Do you?
Yeah.
Well, that's because you're making up for other mistakes you made. Okay, so there's the basic idea of a sketch. So to create something, why don't we create it right in 3D? We create in 2D, so we create a shape. We essentially create a closed loop. So if you ever can't extrude something, it's because your loop is not closed. So it's looking for something that is totally enclosed. If it's not totally enclosed, all the lines are not connected, you can't extrude because it doesn't know what you're working with. So sometimes you can't see that all the lines aren't connected. So there is an option when you go in. Let's just go in here. I just double clicked on that. And okay, this is the original drawing. So what I'm going to do, that line is green. I'm right clicking on it. It's not going to come up because it's already closed. So if that loop isn't closed, there's an option to close loop. And so what you do then is you go around and you click on the next segment, next segment, next segment. And at some point it's going to tell you, oh, there's a gap between those two. Or there's a missing point or something, and it'll help you fix it. When you get all the way around and say loop successfully closed, you can then get out and extrude it. A lot of times that'll be a problem. You can't extrude something or evolve it if it isn't closed. It has to be a closed loop. Like a circle is closed, a square is closed, etc. What time is it?
7:27.
Okay, I-forms. This is something that is really cool. in Inventor, and I learned this a couple of years ago. It's using a sketch not to create a part, but to create geometries, to figure out what the geometry should be. What do I mean by that? Let's supposing we have, and we've had this very thing, we have an arm that has an arm, a hand, we have a game piece, and we need to be able to pick it up from there and put it over here. How long should that be? How long should that be? How long should that be? And how much should they have to bend? Well, you can guess at it, but there's a better way to do it, and I'm going to show you how to do it right now. And it's using what's called I-forms. Let's go back into here. Let's start a new sketch. So I think I can do a new sketch from here. I usually go right up here. On there. Go to the part. And we're going to do a sketch. And we're going to do it on this plane this time. So I'm going to make some joints. Weston?
Why are you, for that specific task, can't inverse kinematics do that too?
Programmatically, you mean?
Well, like, you said to determine how much a point needs to rotate and how long it should be. Isn't that what inverse kinematics is for?
Yes. Are you talking programmatically?
Couldn't you use that for this too?
So you could use inverse kinematics, but it would be very inconvenient. This way, the program will do inverse kinematics for you.
Oh, but that's what the I-form does, is inverse kinematics.
So we're figuring out the length on here also. We're not trying to figure out the angle of action needs to be at, we're figuring out the length of the arms.
Oh, okay, sorry.
Yeah.
So here's some things I didn't talk about. You can, I'm going to start dimensioning this, and instead of giving this a number, I'm going to make it aligned because it's going to change. So it's aligned. So there's my dimension. So let me click on that. So it's come up with a number. I don't want to use a number here. I want to name this dimension. I want to give this guy a name. So we're going to call him, this is the forearm. Forearm, you're going to say equals, and it doesn't really matter what I say here, because this is the part that I'm going to make so I can change it. This is what a parametric modeling program is. It allows you to, instead of just having everything fixed, you can set parameters, and the parameters can be dependent on different things. So they can be dependent on one another, they can be dependent on the way a slider is positioned, for instance. So I want to make this 3. I'm using my center wheel to make that so I can see it. Now I'm going to dimension this one, and again I want that aligned. So there's the length, and there it is, and I'm going to call this upper arm. Upper arm equals, and this guy. Align. This is going to be called the wrist. Now I've given those names so that when I look at in my table, let's see where's is this it here?
I think it's the FX.
I need my glasses. Oh, this one here.
Yeah.
So this is the parameter table. This will come up with, every time you make a dimension, it gives it a name. So it'll be something like D1 or D0 or D2. So it's just a name, like part 1, part 2, part 3. But you can name them yourself. You can use their default names. If you make up names, you'll know what it is. So here's the 3 that I named. So here's their names: forearm, upper arm, and wrist. And it says what they are right now. So I can go in here and change them if I wanted to. That'd be one way to do it. It would be kind of tedious to do it this way. So instead of doing that, I'm going to use what is called I did manage, and now I'm going to iLogic browser. So it's a little tricky to find this. It's under manage and iLogic browser. So what it's going to do is, stretch this out so you see. So now I have two browsers. Here's my model with its browser, and here's my iLogic tab. Now what I'm going to do in the iLogic is I'm going to create a form. What I want to do is I want to be able to manipulate the length of those three things by moving sliders and see what it looks like. So I'm actually going to make each one of those dimensions dependent on a slider that I can physically grab the slider and move it around, slide it around. So I'm going to go down here and say right click, add form. So I'm creating a brand new form. And now over here on the left hand side you can see there's my three named variables. So I'm going to work on those one at a time. I'm going to drag them over here. So now forearm is here. So this is the one I'm working on. So I come down here, the bottom, and I say, here's the option that I'm looking at. Right now, it's a text box. So in other words, much like when we were looking at the parameter tab, we could see the numbers in squares and we could change those. If I do a text box, that's what I'm going to get. I'm going to get a box and I can change the number. I don't want a text box. I want something better. So there's a drop-down arrow, and we're going to pick a slider. And now you see three numbers down here. So I'm going to come over here and click this. And now, this is going to determine my range for this variable. In other words, I don't want this to go from 0 to 1,000,000. I want it to go very specific things. So I will have things in mind. Okay, that'll never be shorter than an inch. And it'll never be longer than 5 or whatever. So I'm going to go ahead and put some numbers in here. So here's the minimum. I'm going to make that 0.5. Yeah, someone has glasses up here. Can someone go get a pair of my glasses out of the box that says Mike? It's on the left-hand side, second from the top, regular reading glasses. So cool. Is that it? There are two of them there? Okay, that's 0.5. My maximum is going to be, maximum is going to be, this is a half hour, going to be 4. And the step size, so this will determine the granularity of when I move that slider. Is it going to jump lengths, or do I want it to be kind of smooth? So I'm going to make that step size 1/10. Okay, so we did the one. Let's go ahead and get out of here. And now there's my form. See the form? I'm going to click on the form, and now it's brought up a slider that I can move. So let's grab the slider.
Because you did 1.1 instead of 0.1.
What's that? I did 1.1? What's the matter with me? Anyway, so I'm going to edit the form. See that? Right click, edit. Go back in. Click on this. You happy now, Sammy? Click on the form. And now I can change that thing, and everything else stays the same. Now I can make one for all three of those lengths. I could make one for each of the angles in there. So I could, just by, and what this form would do is it'd come up with more sliders. So I can keep playing with those sliders very quickly and see what the numbers are and figure out, oh, it'll never be less than that, so it needs to be about that long. In other words, you're just doing a whole bunch of deduction just by you're using the sketch tool, but I'm not making a part. I'm just making some geometry and I'm parametrically controlling it. That's with the iForm browser. So that's an important thing and I use it all the time, especially in the beginning. Okay, because you can't just, I mean, you can take 2 sticks and clamps, and clamp it and try it there, and clamp it and try it there. It's so much easier. So much easier. So learn how to do this. Now we've done, let me see if I can pull up. Now I'm gonna open something that is not in my project. Shame on me. But there you go. Oh, good. So that's the model. There's the browser. There's the form. See, I got all those variables on here. So this is for picking up the ball. This is what I used this year to try and figure out how long our different sections of the arm should be. So I can come in and change the length of that one, change the angle, change the length of that one, change the angle of that one. I think that was hooked up. Change the height of the base. So you can see how that can be a very helpful tool without using any hardware at all. Just going in here, setting up a sketch, naming the parameters, attaching them to sliders, and then just start playing around. You could even build a game piece, and you can see I have a chassis there. You could build a game piece and bring it into here to see what it looks like. So that's the iForms. Have any of you ever used that?
Philip did.
Philip did?
Other guys.
Okay, that's parts, because I think we covered all of that. So let's go to drawings, and I actually showed you, we talked about drawings already. The main thing about doing a drawing is, when you bring the part in, you're going to have to scale it probably to fit on the paper, especially if you're printing on A-size paper that we can print. You're going to have to play around with the scaling to get it brought in the way you want to. And then you create enough views so that by looking at those 3 or 4 views, you can fully understand the part. You don't want anything hidden. So your base view is important, which one you pick for your base view. You don't want to pick something weird, and you don't want to make it so that you can't see every detail of that part. Okay. Assemblies. You can do a lot of cool things. Let's see if this works. Can this be a miracle? I don't think they need it. So this is an animation of an assembly. Think that would help people know how to put that meat grinder together? It takes a little bit of fiddling to do that. And there it is, the section 2 is running. See the hamburger running right through there.
It's disassembled.
You're disassembling the hammer, that's right. So there's a lot of cool tools that you can do. 7:42, oh my goodness. Okay, let's go ahead and take a break, and then, yeah, take a break. A quick review, and I'm going to be reviewing this stuff, and you're going to say, I never heard that before. And you just heard it 2 days ago. So, pay attention. And we're going to go further after we review. We talked about drafting, and I showed you the old tools of drafting, and then you used to have to do everything on paper. And we talked about why you use a CAD product. The product we use is Inventor. And I'm going to start getting specific now when I talk about things that we talk in general about CAD. Well, the CAD that we use is called Inventor. It's by a company called Autodesk that has been around forever. And there are other CAD programs out there. Several of them, SolidWorks is a big one. There are some that work from the cloud, like Fusion and Onshape, where you have to be connected to the internet. We don't want to do that here because our internet is not that reliable. That's why we use a product that we downloaded. So there are lots of reasons to use it. It makes us more efficient, more productive. We can communicate with it. These are some of the tools for drafting. And by the way, last time Gary, Amber's father, had an eraser shield in his pocket. He pulled it out. Who has an eraser shield? Now we looked at this drawing. This is very generic. You know, it doesn't really name anything. So CAD is in the middle. And then if we want to do 3D printing, laser cutting, engraving, CNC, the router, the water jet, or even to print things, this is kind of the generic structure. But in fact, you won't be dealing with that. You'll be dealing with actual products. So this drawing gets a little bit more complicated when you start naming things. It starts to look like that. And this is the reality of what we use here. This is what we use here. So you're going to learn these tools one way or the other. So there's Inventor in the middle. That's the CAD program. And then everything we do in the outside starts with CAD, except for a few things. It's possible to use, for instance, here, for the laser engraver, we sometimes use SVG files. So these SVG, DXF, STL, those are file extensions, right? File extensions. So if we want to laser engrave something, we might start with Inkscape and get some kind of an image, which you can't do in the CAD program conveniently. Or if we do something in the water jet, you can that'll also take an SVG input. And that's just a different format, right? Different format file. So let's just start going around here. We have a bunch of things up here with 3 different Curas for 3 different printers. So we have 3 types of printers. The X-Max is the bigger one you see with the cover on it there. That is a medium grade printer. You can print cool things on there like really fine TPU, and you can even print nylon on that one. That uses its own version of Cura. So we talked about last time we had Slicer there. We talked about a Slicer. Cura is a brand name for a slicer. So it has its own version of Cura. I don't have the name of it right now. And then our print mill, which is the one with the conveyor belt on it, that printer, it has its own slicer because it doesn't use a regular square table. It uses an endlessly long table. So that takes a different slicer. And it's still made by Cura, but it's a different product. And these products will be in the task, it's called taskbar down below. They'll be in the taskbar. You just have to pick the right one. If you're printing on the Ender or the little Delta Minis in there, we have several of those, then you use a different version of Cura again. These all show that this is how you get it from Cura to the printer. It's a USB memory stick, those three. So that's the printer side of it. We have one more printer, it's called the Mark Forge printer. That's the one in the end cap there with the gray one that opens up. That's the really expensive printer. That prints in nylon that's impregnated with carbon fiber. So we don't start using that. We start with the printers that use the cheap filament. So you can buy the cheaper ones. The PLA filament is maybe $20 or $22 a roll. For the Mark Forge, it's $183 for a roll of filament. So we want to make sure we have that part right before we use it, before we print the expensive material. So we iterate with the cheaper material, keep using it. It won't break right away. It won't last very long, the PLA. It will break. But we use it long enough to make sure we got the product right. So the Mark Forge printer, it has its own slicer. And it's a website. So hence the cloud. So it's actually in the cloud. So we have to send an STL file up to the cloud, to this Eiger.io account. We log into that. We're using Steve Dalcher's account that we got the printer from. And then it talks to the Mark Forge. It kind of monitors it live as it prints. So those are all 3D printers up there. 3D printers. Over here, we talked about printing. We print the paper. We use that for things like if we're going to make something on the mill, maybe, or we're going to use lay out holes in the drill press or something like that. We would use that. The water jet has its own slicer, and it's called a WAM. And that again is in the cloud. So you have to go into the wam.wazer.com. You have to sign in, and then you put your DXF file out of Inventor into WAM.
Is WAM also called a slicer?
It is a slicer, in fact. Well, no, it's not a slicer. It's a post processor, is what it is. So a post processor takes your file, your image file, your 3D file, and it prepares it for whatever the machine is. Now for 3D printing, you know, we're using all, yeah, these are STLs, that's right, yeah. Those are all STLs. Yeah, and these do slice, because the way a 3D printer works is it prints by layers, right? Layer, up, layer, raise, thousands of layers. So that's why it's called a slicer. For the water jet, it's just going to cut through. It's going to go all the way through. There's some things you can do to make it kind of engraved, but in general, we're cutting a silhouette out. So that's what WAM does. It helps you, it has a whole library of materials there and thicknesses of the material to help you get the speed right. The water jet basically is a one parameter machine. It has water and it has abrasive, and it's shooting that water through as fast as it can. How fast you move the head is what you change. So in real thin material, you move faster. If you're using a thicker material, and that'll cut up to a ½ inch steel, you just go slower and slower. It has a punch-through time. In other words, you just can't start cutting with it. You have to punch through the material first to get a hole through there. Once you have the hole cut through, so it stays in one spot until it gets through, then you're cutting on the edge. So you cut through, and now you've got this exposed edge, and as you move along, it's kind of cutting off of that edge by shooting water that has abrasive sand, essentially sand in it. And we have a whole pallet of sand out there of the special abrasive. And then so that water, as it's going through there, it's loaded with abrasive. And it's something like 4,200 PSI, very high pressure. And it's got a cover on it to protect you from the splash and everything else. So it basically it's going to shoot through, and the speed is determined by the material type and the thickness, and WAM helps you figure that out. So then you go from the WAM site, which you access on a computer, use a USB port, etc. Justin, if you want to pull your programmers out and do programming, that's fine with me.
Okay. Programmers want to go program?
Yeah. Sure.
Because they don't understand this stuff at all.
I make it
Okay, now that the programmers are gone, we can talk at a higher level.
No, please.
You don't have to slow things down. We'll just keep it out. So here we are, we just talked about the water jet. Now down here, this is what we're going to talk about later this evening, is Inventor CAM. So, and we'll go through the slide and talk about that, but we basically have two machines that use Inventor CAM, and that is the Tormac CNC, which is the one on that wall, and then the Omeo router, which is the one that's right in front of that other mill. It's that low table. So those use Inventor CAM, and you use a different post processor based on the characteristics of the machine. So we'll show you how to do that when you actually do that. Then for laser cutting, that's over here, you have a laser cutter. This is the 80-watt one. And we have what we call a laser engraver. They're actually both the same. The difference is the power that they have. So the 80-watt one will cut material. It'll cut right through. And it works like the water jet. We're laser cutting right through. Go all the way through. If you're engraving, you're doing more like wood burning, where you burn the wood and do a nice little design on there. So by using a lower power and going a little faster, you can actually engrave images, which Ian did last year. He did images of you guys. So that's that. And then, as I said before, we might get an image out of Inkscape or Corel Draw or something else, and bring that in SVG form. So that's the whole thing. Looks confusing when you look at it. A couple things is, one is, this is connected in Inventor. It's actually a tab in Inventor. CAM is. That's in the cloud for the laser. That's in the cloud for the Hydra. These three programs run on the same computers that have the CAM, the CAD software. So they're all on there. ImageBurn and RDWorks run on the laptop that is sitting right in front of the laser cutter. So we'll get the DXF or whatever out of CAD, put it on USB, take it over there, plug it in. And then that laptop, you can't run them both at once, because that laptop is directly controlling the laser cutter or the engraver. Whenever you use the laser cutter engraver, be sure to turn the exhaust on, because it burns wood, it burns plastic, that's how lasers work, and they put off a lot of noxious fumes. So, and we don't cut polycarbonate on the laser cutters. It makes a terrible, toxic film. And now we have the water jet, it would be perfect for the polycarbonate. It just cuts through the
So, in Inkscape, are you using that just to create pictures? Or is there some sort of specific thing on Inkscape that's for laser engraving, or is it just for pictures?
No, it does. Inkscape can be pictures or images or fancy text or whatever. It's just another way of creating things that you can create your image, which you can't do with it.
Okay.
Inkscape, again, is a free program. It's out there. So we talked about the advantages, and we talked about 4 different areas. Projects. Project is when projects, parts, drawings, and assemblies. So projects, that's where you set the location of where your file is going to go. All of our files go on a network drive that is called TrueNAS, and that has a directory called GrabCAD. On some computers it comes up and says CAD files, I think. I'm not sure why it does that, but it does. It's the same place. And then you pick basically your build season. And then don't just shove everything in there. Don't be afraid to create folders out there that say intake or whatever. And if you just want to do your own practice and you're just messing around and there's nothing for the shop to learn it, on the Gears NAS, which is another network drive, there are student folders. So So they actually have student names in it. So you can create a folder with your name on it and put your own thing in there. Now, set the project so it points to that. That's the first thing you do. And then you're working in that folder. You can do that. If you're doing something for the team, if you're looking on the robot or some project around here, everything goes on TrueNAS. And then we talked about parts. We talked about the 3 planes that you work in. And you pick one of those planes to start with because you're going to be working in 2D when you're doing a sketch. So you have a flat piece of paper, you're going to draw on that piece of paper. Is that one of the sketch on the right there? So lines and whatever. And we talked about ways to use I-forms. You know, if I point to the screen or the laser, you can't see it. We talked about I-forms where you use a sketch like this and you name all the parameters of the variables and you can actually drive them either with a text box or a slider. And I actually showed an example of that. And we might do that again this year when we try and figure out, okay, how do we move that from there to there? How long does this need to be? What angle does it need to swing through? Or whatever. You can make that very elaborate just in a sketch where you never make a part on it. You're just using the lines of the sketch. And then we talked about the browser, which is on the lower right. So this is the browser, what it looks like for an assembly. So these all have you can actually name these if you want to. Instead of saying sketch 1, you can actually click on that and name it. Or else it'll say extrusion. You'll have a lot of them to say extrusion. But you can name those if you want to. Now the part, which is this, are not there. The base component, okay, there's the base component. This is what I'm going to show you this a little bit later. This Geneva drive, this Geneva mechanism. These things are named. And then if they have a plus sign next to them, you click on that plus sign, that will usually show you the sketch that part was made for. So you can go in, if you want to change the part, you can't change the part directly, unless you can, if you sketch right on the part. But you can go back into the original sketch, or you can create a new sketch on that part. And that's how you get to those other sketches that are associated by clicking that plus sign. In fact, here's one. See this guy? The drive components. Here's one of the sketches. And every place you see this origin, remember we clicked on that before? That when you click on that, you get the 3 planes and you get the 3 axes. You can pick them up and make them visible if they're helpful to you for doing drawing. Everybody following along? Remember we talked about this? There's a part. That's part of this Geneva mechanism I'm going to show you. This is a picture of the constraints. So we always want to constrain everything. And it turns white when it's constrained. And when it's not constrained, that means you can move parts of it. So you might accidentally move parts. Like if you pull in if you make a rectangle, certain size, depending on how your constraints are set, it might be fine. It will be a rectangle. But if you grab the corner of it, or if you change one dimension, it'll turn into some other object that doesn't have parallel sides because it wasn't constrained. But if you use this little guy, which I just learned about, it'll fix all your constraints. In fact, I had one today. I just drew a simple box, and it looked constrained to me, but it wasn't white. Now, what's wrong with that? I had the dimensions on both legs, both sides. I had a size of a hole. I had the hole located, but it said it wasn't constrained. And sure enough, I grabbed the corner of the box and I moved it and turned it into a diamond. So it wasn't constrained. Because the sides were not set to be parallel and there was not a perpendicular corner in there that held its shape. So you learn something every day. But then you can forget it. Okay, this is a drawing. We talked about drawings. And this is a typical, when you used to do drafting, this is what you did. You did a front view, a top, don't point at that. You did a front view, a top view, and a side view, and then an isometric view for clarification if necessary. Sometimes you just look at the front, top, and side, you can't figure out what shape is that. This way you can actually see those lines. So isometric view if necessary. And then this is your title block where it has the material, the date of the origin, who did it, it was revised, revision number, etc. Also it has the scale. Then we talked about parametric modeling. And I'm just going to get out of here and I'm going to show you. Stop. Okay, I'm going to do a new drawing. I'm just going to create a new part. This is the way I do it. I'm going to start a sketch. I'm going to pick a plane. And now I'm going to do a box. And now you see that one of those dimensions is highlighted. So that means it's ready to be changed. If you start typing, that's what you're typing. So I'm going to pick that as my base dimension. I'm going to call it base. You see it's red, so I'm not done. Equals, still not done, 2. Turn black, so that's an acceptable value for that thing. Now I'm going to use that base as the basis for all my other dimensions. So this is what parametric modeling is. You make dimensions dependent on one another. So this dimension, and by the way, these funny lines you see around here, these are constraints. What is that one? What constraint is that? Do you see where my thing is? Why is nobody answering?
Just makes it
Perpendicular. We have fancy words for this. The programmers are gone now. You can use it. What is this one? Parallel. So these two are parallel. These two are parallel. What is this one? Yeah, it's actually yeah, normally it would be horizontal, but it depends what reference you want to create. But yes, one's horizontal, one's vertical. You're not always the one you think it is. Okay, so now we're going to go to dimension, and I'm going to dimension this line. And so now it knows I'm editing it. If I click on it, now I'm in the box. So what I'm going to do is I'm going to set that dimension equals this dimension times 2. Okay, that's that one. Now I'm going to do a circle in here. Here. And that dimension right here, I'm going to have to stop this because I can't jump to another dimension. I must be able to do that. Forget I said that, that would just be confusing. So now we're going to take this guy, and we're going to say divided by 3 is the diameter. And now we're going to do, so you see where it says fx? That means that is a derived dimension. You can't actually change that dimension. It's dependent on another dimension. So now we're going to do, we've got that one, we've got that one. So now let's set up where this hole is. We're going to go from there to there. And we're going to call that this divided by 3. And I'm going to say this. My dimension box is still in, so it's still in dimension. And then we're going to do this, and we're going to say this divided by 4. So now it's all white, it's fully constrained. There's only one dimension that will change everything, so I'm going to go in and change that. So this dimension right now is 2, so let's make it 3. And everything changed and kept its relative reference because I used formulas to derive all those other numbers. That's the power of parametric modeling. So what that means is if you've got a hole and a pin and you make the pin 5 thousandths under so it fits in the hole, if you make them dependent on one another, if you change the size of the hole, the pin size is going to change too. So you'd have to go back and figure that out, and it's going to keep the same tolerance. So that's what the power of parametric modeling is. Any questions about that? This is good stuff. Now that the programmers are lying.
Is it possible to correlate 2 models to where they'll do that? Like
Yes.
2
Yeah, if you're in the same project, so you've got that FX at the top, the parameters, anything that's listed in there you can relate. And if you're in the same project, you can, yes. Or particularly in an assembly, that FX table will have everything in the assembly. Then we're going to talk about assemblies. Now we haven't talked about assemblies too much. So we talked about sketches. You extrude that or revolve that and you make a part, and then you extrude through it or whatever. So now you've got a single part. An assembly is parts put together, because all of our robots are parts that are put together. We don't want to make the robot a part, right? Because you could. You could just take this part, keep building, extrude wheels on it, and extrude a chain, but nothing would work. And it would be really hard to manufacture. So you want to make all your parts separate, and as much as they're usable. So this is, okay, we talked about this. Now one thing we didn't talk about, we talked about projected geometry. Let's go back. Projected geometry. Driven dimensions. Yeah, this is something that I didn't get for a long time. Way back in the beginning, we had a really smart mentor. His name was Ket Baumgart. Aaron's brother. Anyway, he's a young guy. He was so smart. He's the one that got us all the animation awards. Anyway, he figured out Inventor in about, I think maybe took him 3 minutes or something. I don't know what it was. It was ridiculous. If you go into, so let's go ahead and finish this sketch, because I can't do anything until I finish it. And I'm going to extrude it to make it a plate with a hole in it. So I'm going to go extrude. I can also right-click, extrude. This is what I'm going to extrude. You see the hole is not lit, so I'm going to leave the hole there. If I selected the hole to it, it would turn green, and there wouldn't be a hole there. So we're going to extrude that 1 inch, which is what it said there, so it extruded 1 inch. So now that's done. Now let's suppose I want to sketch. You see that surface is lit. I'm going to right-click, new sketch. Now let's suppose I want to put a ring around this, and I want to extrude a ring out of it. Now the problem is that this sketch is not in my new sketch. All I have is that surface. So like if I try to, I don't know why that normally have to do is you have to say project geometry. This guy here. And what that means is anything that I click on. Oh, wait a minute. So let me look at this. See, I can't see the middle of that hole. It's not finding it. So I can't make a hole on top of it or a ring on top of it. So now I'm going to go project geometry. Project geometry. Project that there. Now you see the center? Now it's part of this drawing. So now I can go back. And now I have these two lines. The one I drew and the one that I projected. So because both those, I believe both those lines are there, I can actually extrude that donut. So let's get out of here. I'm going to right click, extrude that. And I didn't draw that inner circle. I just projected it from the other drawing. So that project geometry is very useful. And evidently it lets you do dimensions off things that are there that aren't projected into the drawing. So that's projected geometry. If you ever get lost, you know, like if you're working on two sides of a frame, you can project from anywhere that you can see. So one thing we didn't talk about was views. So view is the way you look at the drawing. And this visual style is the way you change the way you look at it. Now you can't, on a 3D object, you can't see inside of it. You may be able to see if you turn it right, but you may not be able to. So what you can do is, you can pick, for instance, a wireframe view. Now, all I've got, it's as if it's made out of wireframe, and I can see the whole thing. I can see that inner cut goes all the way through it. And I can see anything that's on the other side of it that I can't normally see. Now, you don't always want to use that. You can use that if you want to. And there are other things that, you know, like make it look cool, like let's do make this in watercolor, or technical illustration. Now I have this set to dark mode. That's why I like background. I like the dark mode. It's easier on your eyes. That's in the application settings, I think. So under manage, there are two tools. There's application settings and document settings. Application applies to the whole thing. Document refers to the one you're working on. So that's where you set your units. There's all kinds of tabs. It's just, we're not going to get into that weeds and that. So yeah, and if I just hover there, I just left the mouse there, it shows me what that view is going to look like if I choose it. Shaded, realistic. Ooh, man, so real. You can almost feel it, can't you? Okay, so I talked about projected geometry. So now I want to talk about driven dimensions and assemblies. So I'm going to, any dimension that's out there, you can not only use it to build other dimensions off of it, but you can drive that dimension. That means you can change it. And I'm sure I can change it by hand, or I can put a slider on it, an I-form, like we did. But you can also animate the change. You can say, change that value from this to this, and do it at this speed. So then you create an animation, which is kind of cool to see how things work. So I'm going to go ahead and create an assembly. A new assembly. So that means, so I end up, there's a blank screen, there's nothing in here. So what I have to do now is I can place. Now I can either place a part that I have, that I've created, or that I've imported, or I can place something from what's called the content center. The content center has common parts like screws, washers, nuts. If you want to do that, you can do that. But mostly we do parts that we're gonna. So I'm in this drawing, so I'm gonna bring in the base. Now, it always comes up with, okay, there's an option to put another one in, right? So I got one, there's another one if I want to do it, I can bring multiples. You get out of that, you press escape. Now, in an assembly, you don't want your parts moving all over the place. You're going to constrain them together, but not only that, you want one part to never move. And that part is called, it's grounded. So if I right click on that part, I can say grounded. That is the part that is grounded. Only ground one part in an assembly, but do ground one part. Otherwise, when you start moving things or you rotate things, the whole thing will just start moving around. Now, this part will never move. It will stay locked in that orientation, in this position, in relation to the origin, in this ground. I'm going to go get some other parts. There's a good one. I'm going to get that one, and I can do more than one. I've got two of them. And I'm going to get that in as well. So I'm getting three parts at once. I'm going to bring them all in. There they all together. So it's allowing me to make a second set. I'm going to escape. So I've got three parts that I brought in. And they're all, you see, they all move around freely. And they all have their own orientation depending on how they were created. So we're going to put these parts in this thing. So I'm going to take the way I do this, there are several ways to rotate. One is to go over here, this little guy. You click on him. Now you've got your rotation circle. Because you're always ready to rotate things when you place it. So what I do is I hold F4. It's just a habit that I have had. So I'm going to turn this around here. I think this is the one I want to put this thing in that hole. So it requires this piece will not rotate because it's grounded. This piece I need to rotate, but I just want to rotate this piece. I don't want to rotate the whole drawing. If I just do the F4, I'm changing everything. So what you do is you click that part, and this is hard to remember, you press G. Don't ask me why. The reason you press G is because it works. There. So remember that. Now this part will rotate. So what you want to do is get it close to the way you want it. And it's going to be something like that. You don't have to get it exact. You just have to get it within that 180 degrees so it doesn't flip backwards on you. It's going to constrain itself in when I start applying constraints, but it needs to kind of know which way to go. So I'm going to take this thing, hold that F4 down, get on the bottom side of this, and I'm going to constrain. So I can hit C for constrain. That brings up the constrain box. I can also hit up here. Here it says constrain. You see that? You can also click there if you want to. You can also you see constrain, there's my constrain box. Now it's looking for me to tell some things about the constraint I'm about to apply. What kind of constraint is it? What kind of constraint is it? So this one, this little box up here, is for putting two flat surfaces together. So you can either put them together like this, or you can put them together like this. So they're in the same plane. But you can make them face to face if you want to. So that's what this box on the down here shows. You see there they're face to face, and here they're in the same plane. So this is the kind of constraint that I want. And this is regular, actually this is a concentric constraint, so I'm going to use this one. Because I'm going to use this little circle here. And you see the center line appeared there? So when you constrain something that has a round hole in it, you only need two constraints. You need to constrain the center line. If the center line is in line with the other center line, that takes care of the x and y. Now you just need to do the z. You just need to get some surface down flat. So here's I'm going to take that one and I'm going to go okay, there it's now. So now I'm going to move this around again. And I haven't said okay yet, so that's not locked there yet. And it looks like it's there. Putting this thing together. No, I'm not. It doesn't go there. It goes in the other side. So I got out of that. So I'm going to put this. I'm going to constrain C, constraint box. I'm going to do this cylindrical constraint. I'm going to pick this ring and I'm going to put it on this side of this part. So now it's laying out here. Now I didn't say OK yet. When I say apply, then it will be locked there. So I'm going to say apply. If you say apply, it will allow you to keep using that constraint box. If I say OK, it will constrain it and the box will go away. So I'm going to say OK in this case. Now, let's see if I can move that around. Oh, look, it spins. Why does it spin? Because it's not locked in place. I allow this to turn by lining up the center line. So they both have the same center line, so this is going to rotate around it. But notice it's locked down to this surface here. See? Did you see what this shows here? See that little tack?
So it can't move up and down?
That shows your grounded part, that tack. So this part is grounded. It can't move up and down because the two things that I chose to lock together, they are together. Those two circles I chose, circle on this part and the circle on that part, they're right together. So I lined up the center lines and then boom, those two lock together. So that part is locked on there, but it still rotates, which is what I want. I want this to rotate.
If you weren't going to rotate, how would you do that?
So I would have to come in and do some kind of locking, like one of these flat surfaces, a certain distance from that. There are different ways to do it. Sometimes you actually have to put a feature in there that you're not actually going to use, like a little bitty flat surface so that you can use to constrain it. But in this case, usually round things you want to rotate. So now we've got that in. So now let's put this guy in. And he goes in the other hole. Now I can see that I've got that constraint. See what it's supposed to look like. Stop. Control Z. Just be on top of it. That's right. You can do Control Z as many times as you want to. So I've got it the wrong place. this does go on the other side. So now when I go over, so I light this part. See, when I highlight that part, you see this is on the left-hand side of the browser. See that's blue? So that's the part I'm talking about. Now you see the plus sign? If I hit the plus sign, it's going to show me the constraints that are on that part. So I'm going to delete that constraint. And so now it's free again. And I need to be on this side. So I'm going to constrain this in 2 steps this time. I'm going to constrain the center lines. You see, any one of these circles that I take, they all have the same center line. You see that? So I'm just going to take it. Anyway. Now the center lines are constrained. So this will rotate, but it can move up and down. Whoa, why doesn't it move up and down? So I think what I'm going to do is I'm going to constrain this surface to this surface right here. So that's the surface. You see, this is just the edge. That's the other edge. This is the surface. I'm going to constrain that to the bottom side of this. Now you see what happened? I constrained that to that. But look where the part is. It still moves around. Why is it still moving? Right. So the constraint that I applied is still holding. So what I didn't do is I didn't line up the center lines. So now I'm going to do the center lines. Center line, center line, apply. There it is. Escape means get out of what you're doing. No, it doesn't. No, it doesn't mean okay. It means not okay. You're not hitting okay if you do that. But if you've already applied it and hit okay, then yeah.
So if you apply it and hit escape, is it the same?
It's the same as saying okay. Now just watch this is good. Does not move. This is the last one we'll apply. Why is that happening? So here's what I'm going to do, because I don't know why it's doing what it's doing. I'm going to temporarily suppress that constraint. So I can suppress it without deleting it. So that constraint is no longer in effect. And now it moves around. And is it staying in the plane that I think it is? You see, I can move it. Oh, no, it's not staying in that plane. Oh. Everything I'm teaching you is wrong. So when that happens, I just lost that part. So I'm going to go up here, this box, and I'm going to hit the home button. What the home button is going to do, it's going to open up your screen so that all the parts that you have are visible. They're now on the screen. Now, they're mighty small. Here's one of them. What's the other one?
She ran away.
So remember that, you ever get lost, you lose a part or something, just go home, and it'll open up your screen, I'm doing this on purpose, you know. You guys learn this stuff.
I'm sorry.
That constraint is not suppressed. See, there's no check bar there. This constraint is suppressed. See the check bar? So why does this not do what it's supposed to? Anyway, let's do this other one. So this part, this is a pin, and it goes in this hole. See there? So I'm going to select this part, hit G, so now I'm rotating that part, and it needs to rotate this way. And this way. Now I'm going to line up the center line, constraint C, center line to center line. And now it's the center lines are lined up, but this pin is not locked in. So now I'm going to constrain this surface. The bottom of this thing. So that surface right there. That surface. I think the reason this thing's acting goofy is because I got this part off the draft CAD. I didn't create it. A lot of times when you bring parts in, if they're created in SolidWorks or some other thing, they don't behave properly. So anyway, there, you can see that pin is on there now, and that's constrained. Now, instead of me wrestling with this, because I think the problem is that I brought the part in from SolidWorks, I'm going to go to this assembly that I already have together. So here's the part. Now, these both rotate. This rotates, and this rotates. Now, how do you make that work like this? See what it does? Isn't that cool? So here's the secret. You select the part. Let's see, it's kind of, here's the pin. Here's the pin. If I right-click on this, right-click is your best favorite friend, you're going to see that it says contact set. So in CAD, if you have things out there, you can just run them through one another, whatever. But if you put two parts in a contact set, when they touch, they won't go through one another. They will hit and start moving. So this is, that pin is checked as a part of a contact set. And then I'm pretty sure this guy, he's right here. I'm going to hit the plus sign. I'm going to right-click on him. And he is also part of the contact set. So these two parts are part of the contact set. So if I rotate this thing around, no, it's because I didn't align it. When it gets in there, it's going to hit this edge, and because I'm rotating this one, it's just going to push it. Is that cool or what? This is called a Geneva. It's called a Geneva mechanism. That's because there's one of these inside every Swiss watch. Okay, that was a joke. Okay, now I put this whole thing together to show you how to drive a dimension. So there is this option to see this drive. I right click, look at drive. Now what it's going to allow me to do is to, because this is going around a circle, it's measured in degrees, so I got it set to start at 0 and go to 360. And it's going to take, it's basically, there's no pause in between. So as it goes, it's going to go as fast as it can go. I can slow it down. What's slowing it down now is the latency of the computer. But I can slow it down by making this 100th of a second or 1,000th of a second or 10th of a second or whatever. So now let's, you see the play buttons here? So now let's play it.
No!
Why are you not in time?
What?
Like, if you're going from 0 to 360, that's the same spot, and just did it already.
No, because the computer can't do it that fast.
So then, what is going on when you hit 0? Isn't it you telling it that there's no flow rate?
So there's no delay in there. That's as fast as my computer can do it. We're doing a lot of calculations in there. I can make it go slower. I can't make it go slower. The reason it didn't work last time is because I was driving the wrong dimension. So there's an animation just by using that very simple drive function, by driving a dimension. What I'm driving is the rotation.
So the pause delay, it isn't like how long it takes from it to go to 0 to 360.
Let's make Sammy happy. We want to make everybody happy. We put a delay in there. But to make it dramatic, we're going to put a 1/10 of a second. And you could just watch this all night.
Yeah, it's even cooler and slow.
Oh, it's 7:30. Okay. All right, let's stop there and take a break. And we have yet to cover the topic of the night, which is CAM. So take a break. I always use this drop-down box between these four, but you can also click on the box itself. That brings up this, which you'll see in most tutorials. This is just a bigger view of it. So we've talked about sheet metal. On the other hand, we're not going to talk about it. So let's go back to this box. So there are 4 things in here. We talked about parts, which you start with a sketch, and then you extrude. And then we talked about putting parts together into an assembly. We talked about making a drawing if you need a physical representation of what you're doing. And the other thing in here is this presentation. So this is kind of a cool thing. Presentation, what presentation is, go back here. Anyone know what that view is called? So what is this called that we're looking at? Anybody know?
It says exploded view up there.
Oh! One person can read.
I said it before I knew what it
Oh,
was.
did you? Wow.
Yeah.
Whoa.
It is an exploded
That's
view.
pretty impressive. for
It's
me.
because it's your birthday.
Yeah, it is my birthday.
And it's not because someone put C4 in there. It's not that reason. It did not explode. But you take it apart so you can see how it's built. Now, often when you buy things like a key is a good example where they have no instructions, it's all pictures, they're all exploded views. So you can see how the thing goes together. So this is called a presentation in Inventor. So you can take any assembly and if, you look at it because you designed it, so you know how it goes together, but to make it so other people can know how it goes together, you can create what's called a presentation. It's very easy to do, and we're going to do a short one here. So here is, this is actually an assembly, right? We got 3 different parts. So if you look at it, you can kind of see how it goes together. But let's make it dirt simple. So let's make a presentation out of this. And you do that by going up to the little box and saying, presentation. We want to use this guy. Now what it's done here is it's created, it's given me the opportunity to create a timeline. So it's like a movie. In a movie when you do like, if we participated in the animation award, we would build a storyboard. You know what a storyboard is? Where you actually have drawings. Each page tells, this is what we're going to do here, this is what we're going to do here, what it looks like on the sketches. It's called a storyboard. And you'll have, every time the scene changes, you have another page in your storyboard. But you can create that here by, as you do the explosion, the exploded view, you take snapshots. So the way you start taking this thing apart is you go to here, and you say, tweak components. So now it's looking for me to pick a part. I'm going to pick this part. Now it's allowing me to move that part around, and I can move it at a certain rate. So what you do is you grab the arrowhead right there, and now I can move that up. And this little box here says how high I'm going to move it. So if I'm happy with that, I can say OK. OK is down here, the green arrow. So I could also rotate it if I wanted to. I just moved it. And you can also create these trails that don't, if you offset it. In fact, let's see if we can offset it. Yeah, so if we offset it. See the trail there? So we went up and over, and then you can do when you animate this, how long do you want it to take to move that part? It's going to stretch out that move that I did, that double move. And right now it's going to be 2.5 seconds. So that's fine. I'm going to say OK to that. And when I did that, these are the 2 sections right here. So we did the up move, and there's the over move. So if I now run that, here's a little pointer. I'm just running it by hand now, up and over. And I think I can actually play it. It goes up and over. Is that cool or what? Let's hear it. Let's hear it. Okay, now we're going to move this guy. So I'm going to tweak the component. And actually what I can do now is with this picture, where I am, is I can I can capture it. Okay, so let's move another part. The tweak component. So I'm going to move up. And I'm going to move it this way. You know what? I'm going to undo that. So control, because I see I left this button down there. Cancel. Cancel again. And I'm going to select both of these. Now I hope it moves together. Stay there. You go there. And go over here. And that's going to take 2.5 or 97 seconds? No. Where's the duration? What happened to duration? Anyway, I can change the duration down here just by dragging this out. So to do that, it's going to be uneven for those two parts. So now the last part, I'm going to move this part. Go up. There the duration is again. Okay. So now let's see what we got here. Let's say. Now, in between those motions, you can actually rotate the view if you like to. So get a clearer view of it. Now, you think you have the whole robot, and you can actually take the whole robot apart like this. Animate the whole thing. You know, you make it go a little bit faster so you can see it. But would that be impressive or what? Yeah. That's impressive. You can take it apart faster this way than you can with a wrench. So that's called a presentation. So when you get a chance, make an assembly and you play around and create a presentation. Any questions about that?
Can we do that on the robot?
That's how we can move the robot.
I have a question. Couldn't you just change the duration and then it would be faster to get rid of the wrench? If you make everything take like an hour.
You could do that. So you can, in that timeline, you can just drag things around. You can move them, you can make them overlap, do them at the same time. You can stretch them out, shrink them, whatever you want to do. It's just like a movie. So now let's go, that's the slide. That's the presentation. Now let's talk about CAM. Now unfortunately, I don't have CAM installed on this computer because it is a tab in Inventor. It says CAM. We have it on all those computers there. I forgot, I didn't notice that when I was at home working on this. We're going to talk about it. So CAM means computer aided manufacturing. So what does it do? It uses software and computer-controlled machinery. So what is the computer-controlled machinery that we have?
CNC.
CNC, okay, what else?
CNC router.
CNC router, okay.
Laser transfer. It is.
It is, but we don't control it that way. So those are the only two that we use CAM for. So this is really helpful when you're doing multiple things. You know, like if you're doing multiples of the same part, you can just repeat. You know, once you get it tweaked, you just put the part in, start it. Put the part in, start it. Put the part in, start it. So what it does is it creates a tool path, and the post-processor, which is the software that is built into Inventor CAM, it processes the actions that you have set up and puts them into G-code. How many know what G-code is? A couple. Okay. So what the CAM is going to do, now this is somewhat analogous to a 3D printer because when you're working with the CNC, you don't just go in there and take it all out. You do that, what happens? What happens if you just go and try and take the whole thing out at once? Like make a whole hole at once. The tool breaks. The tool breaks because the tools are not made to take out that big. Now, not that Sammy's ever broken a tool. We'll just leave that there. Okay, so here's a picture of what it looks like in the CAM program. What do you think those blue lines are? That's the tool path. So you have to select your operation. You have to go in and do a setup first so it knows what you're doing. So the most important thing about all of these things that we've talked about is the origins. Now it doesn't matter in CAD where you have that origin when you create the part. I mean, it matters, it could be convenient to do other things, but when you get the thing out of there, you're going to send it to a machine. The machine has to know where to start. And you need to know where to put that tool so that you're using the material so you with the least waste, least amount of waste. So you have a big sheet. And we've got examples of big wasted material. People didn't do that. So you get a big sheet, you're cutting out a small part. When you create the CAM, you tell it where you want the tool to start. So typically you're gonna go like, okay, there's a rectangle. I want to start in that corner or that corner. Occasionally you would start in the middle of something, but you need to pick something that's convenient and obvious and something that you can find when you go to set the tool for the part. So a corner is real easy to do, and there's in the setup it has the option to say where on this piece of blank material, because you start with blank material, you don't start with a finished piece. You start with a blank sheet. Where do you want to start? Usually you start on the top surface. Okay? You know, the tool's not going to start in the bottom, it's going to start on top, start going down. And usually you'll start in some corner. And then when you go to set up the machine and the part, you're often restricted on where you can put the piece on the bed because of physical size. So you're going to fasten that piece down, and you want to get the orientation the same way you did it in the CAM. So I'm going to use that corner. I have to know what your X and Y is. Z is always going to be up and down. You have to know which direction is X and which direction is Y. Another thing in the setup, what you set up is you say, this is X and this is Y. You get that wrong, it's going to start in the corner and then go off the board. You've got to get that right. That starting point is the most critical part. So we're going to create basically we're going to create a tool path. We're going to go through setup, we're going to tell it what size the material is. We're going to tell it where the origin is. This is where we want to start. You're going to tell them how thick the material is. And then you're going to go down and start choosing tools to work on features. So a part has features. It has a hole, it has a rounded corner, it has a pocket in it. The whole thing is faced off. Those are different features. It has drill holes. Maybe it has 20 drill holes. So all the features on that piece need to be done, and often it's with different tools. So if you're going to, here's an important point, if you're going to do something on the CNC or the router that uses more than one tool, those tools have to be set up beforehand. You can't stop in the middle and set up a tool. The program doesn't let you do that. So the most important thing about the tool is the tool length. So we have a way of setting the 0, which is the top of the piece, setting the Z. And then we have a way of measuring our tools. Okay, how tall is that tool? How tall is the next tool? If you don't get the height of the tool correctly, it'll go down too deep and start moving and break the tool. It's real easy to break a tool. And you just watch it and it just happens. It's like, whoa. If it's a really big tool, it can hurt the machine. So more often than not, it's just being expense. So you need to get you need to decide how many different operations there are. Is this a drill? Is this a contour? Is this a pocket? Is this a face? What are we doing here? All those different operations will take a different tool. You go into the tool, and you actually have to set up the tool then. You have to say, okay, this is a drill, and I'm drilling a 1/4-inch hole. How fast do I want that drill to spin when I'm drilling a 1/4-inch hole? And how fast do I want the drill to go down? When you're drilling by hand, you don't think about it. You can feel it. You can feel what you're doing, so you go as fast as you can. On the machine, you've got no feel. So you've got to figure out what you're going to do, or know what you're doing before you do it. And on the in PathPilot, which is the controlling software in the CNC, there are sliders there, and the bottom left slider, you can move it all the way over to the left. Slow everything way down. And that's usually the way you start, because you're not sure. And then if it's cutting it right, then you can speed the thing up as you go along. But you need to set up for each of the tools. You need to set up the diameter, so it has to know the diameter of the tool. Otherwise it can't make the hole the right size. So if you tell it it's one size and it's another, like Sam, we did recently, because we thought the tool was 2 millimeter, and it turned out to be a 1/16 of an inch. So when we ran it with the 1/16 of an inch tool, our holes ended up too small. And we're looking at it and said, why are they too small? Well, we lied to the machine about the size of the tool. The diameter of the tool was 2 millimeters. It was a 1/16 of an inch instead of 2 millimeters. You have to tell it the right diameter, and you have to tell it the right length. It has to know where the end of that tool is. Because what it's going to do when it starts is it'll move quickly to its safe distance, and then it'll go down slowly until it's about ready to start cutting, and then it'll start cutting. So if you get that length wrong and it goes too deep, you'll break that tool immediately. It won't be able to cut that fast. It'll start moving sideways and snap that tool off. Real easy to do. So we talked about tools, feed, speed, and clearance. So what's the difference between feed and speed? This is not a trick question. These are real words. Yes? What's the second thing you said? That's correct. That part is correct. So speed is the RPM. Feed can be how fast it's going down. It can also be how fast it's going sideways. So they're actually separate feed rates. The one is called the plunge rate. That's going down. the feed is going sideways. So if you go too fast, essentially the tool can't cut it its way fast enough, it'll just break. It has to be going at a speed that it can clear the material as it's going fast enough so it doesn't overload the cutter and fill up. Now with aluminum, we use mostly single flute cutters. So that means, you know what flutes are. So on the drill there are 2 flutes. In aluminum, we just use single flute cutters and run them as fast as we can. Because aluminum has a tendency to weld into the tool. It gets so hot that it actually melts and sticks to the tool. And that'll happen if it's not lubricated good enough or if there are too many flutes. So the trick with aluminum is after you cut it, you've got to get it out. The cut material, you've got to get it out. So we use flood lubricant, we use air to blow it out of there, and we use single flute tools. So that single flute tool is going to make just one, it's going to take one shaving every revolution. It gives it a good chance to clear that aluminum out of there. Okay, so we're going to generate G-code. There's a line of G-code, and there are several things that you can put. Sometimes there are several things on one line. These could all be on separate lines, but in this case, G01. What does that mean, Sammy? It means go at the feed rate that you specify. Right. And the feed rate is identified with what? What's the command? Yeah, so there it is. The last thing in the line is F20. So that's feed rate of 20 inches per minute. So it'll move sideways 20 inches per minute. And the S there, what is the S for? All of it? Speed, yeah. So it's rotation per minute. Here it is at 3,000. It says 3,000 RPM. And then you're saying T01. What could that mean? Carter? T01. Tool. It has to have a tool number. So in the Path Pilot, which is the software for the CNC, there's a tab called Offsets. That's where all your tools are. All the tools have numbers. And when you're setting up your tool in CAM, you have to do the same number there as you use in Path Pilot. So it knows, okay, this is a 1/4 inch drill. The number is number 4. So you got to use that number so it knows what it's doing. Give it the wrong number, and it'll break something. Okay, what is X1 and Y1? Victor. Okay, what is X1?
X1. Go there.
One what?
X1 summary.
One what? What if it said X2?
Maybe X2.
2 what?
Maybe inches, maybe millimeters.
Right, whatever units are set for the price, right? So if it's inches, it's going to be 1 inch. It could be 2 inches. So X1 or Y1 goes to X1, Y1. And it's not going to go like that, it's going to go like that. It's going to go diagonally to its location if they're both on the same line. If you want them to go separately, you put them on separate lines. And it'll do the first one, then it'll do the second one. And or sometimes you want to do that, because maybe you have a clamp in the way, that if you went directly to the clamp. All right, here's an example of G code in the upper left-hand corner. So that G1 is, as Samuel said, is go at the feed rate that I told you, with the F command. But if you go G0, that means just get there. Just go as fast as the machine can go. I just want to get in position. I'm not cutting, just go as fast as you can. So that's G0. G1 and G0 are modal, M-O-D-A-L. That means once you set them, once you say G1, it will stay G1 until you change it. If you say G0, it will stay G0 until you change it. And the modal commands, so here, this shows exactly what it said. G0 goes fast as it can. Go to X7, Y18. You see the diagonal line? That's the way the head moves, except if you're using a router, that's the way the head moves. If you're using the CNC, what moves? The router and the CNC work differently. The table, right. So the X table and Y table. So the head on the CNC stays the same. On the router, the head is what's moving around. So there's a gantry on there, the X and the Y. So you don't care about that. It is always talking about the tool, whether the table moves or not. It's as if the tool will move. So if you say X1, the table is actually going backwards. The tool will stay the same place. Which is like a parent tool movement 1 inch forward. Okay? So when we talk about it, when we refer to it, when you talk to it, it's as if the head is moving. Even though on the CNC, it's the table that's moving. Just ignore that. Well, don't let it run into something, but that's the way it is. Okay, so there's an illustration of that. This is what it looks like. Here's a bunch of G codes. There are G codes and M codes. M codes like motor codes. So like the coolant is an M code. Starting the spindle going, the spindle for the drill or whatever, that's an M code to start that motor. It's one M code to start it, one to stop it. The speed is a G code. It's a S parameter. But starting and stopping it, those are M codes. So here's the M codes on the right. And every machine has its own set of G code and M codes. So that's why the manufacturer decides what is for this machine. This is the way my machine works. And give it a code that they don't recognize and just ignore it. So you can't use every G code in every machine. You can actually go through and write G code. So it's fairly easy. I mean, even Sammy could do it. That's how easy it is. She could do it. So that's how she wrote her initial Top Gun thing, right? She actually wrote the G code. She came to me and sort of snuck up and said, "What does this mean? How does that work?" In the background, she's going to write music on the CNC. So she did. But the post-processor, if you're using a pen mill to do a big hole, that is a complicated set of steps because the CNC, all the motors there are step motors, except the spindle. The table motors are. So the spindle is a brushless motor that's just spinning. The head movement, the Z movement up and down, the X movement this way and that way, and the Y movement this way, they're run by step motors. That means that instead of that motor just spinning, like the motors do on a robot, and then you're geared down, it turns like real slow. It could have like 4,000 steps in one revolution. So you can tell that motor exactly what position you want it in by the number of steps you tell it to take. And what Sammy notices, those steps make a noise. And if you run it faster or slower, it changes the pitch of that noise. But you're actually hearing the steps, that humming. So that's the difference between a lower end CNC, which is what ours is, and the bigger CNCs, which use servos. This is a little bit of free information. What can happen with a CNC like ours is it doesn't know where it really is. It knows when you told it to go, and it assumes it got there. So So take 10,000 steps in that direction and stop. If you tell it to do that, it assumes that's where it is. If it runs into something along the way and loses a step, that step is lost forever. You can't recover that. So you can physically hinder it so it miss a step. You have to do something like run it too fast and run into something. The servo motor actually knows exactly where it is. If you tell it to go there and it doesn't go there, it knows it didn't get there. And it's going to keep trying to get there. But the servo motors are twice as expensive as stepper motors. So that's why most of the lower end CNCs are stepper motors. Free information. Now we cannot use stepper motors on the robot. It takes a special controller. All right, so there's our codes. So it's like a language, right? So in language, you learn the syntax, you learn the grammar, you learn how to put it together, and then you can speak the language. G code is really simple. You know, we have maybe 40 commands. So there's actually a sheet hanging over there that has G codes on it in the CNC. You can look down it, and if you wanted to write your own G code, you can do that. But what I was saying was about a circle. So if you're doing a pocket, that is a very complicated thing to make it step, step down, down one and over one, down two and over two, whatever, to make that round circle. Well, the post-processor does all that for you. It writes these thousands of lines of G code to make it do a perfect circle. And you can look at it when it's generated, but you couldn't write that by hand. Okay, this is the path pilot interface. Now we said we had two machines that use CAM. One is the router, and the other is the CNC. The Omeo router has a little orange box under there. The little orange box is the controller, and it is interesting. So it doesn't do exactly what we expect it to do, but we figured it out. This Path Pilot, this is a program that Forma actually wrote, specifically and only for their CNC. And this runs on a Linux box, so you can't get in there, you can't get the operating system. The problem with Windows is it's a business operating system. So it decides what goes first. You put things in a queue and go through them. When you're controlling machinery, you really don't want Windows making decisions for you. Because when you want something to happen, you don't want it to happen 20 milliseconds later. You want it to happen now. And that's what Linux gives you, that kind of control. That's why we run this runs on Linux, not Windows. So here's this interface. It looks like a lot of stuff. What you're looking at in the upper right-hand box is called conversational code. So what we've been talking about is using CAD, CAM, and a post-processor to generate G code. So we did that for fairly sophisticated things. If we have something real simple, like 20 holes in a row, all same size, or one big hole that we want to make, or we want to thread a bunch of holes, we can use what's called conversation. You don't have to use CAD. You don't have to use CAM. You're right in this screen right here. And all these things along the top here. And these things up here, this is what you can do. And we're looking at the threading. So it has you just fill in the parameters of all these white boxes. And if you fill all those in, and then you tell it where to start, G54 is an origin reference. That's the normal, G54 is the normal reference system you use. There's other ones, G55, G56. Like if you had to turn a card over, you have to put a different reference. So there it has where to start, use G54. And there's the tool number 10. There's the spindle RPM, that's an S. There's the feed rate, 20.3. There's the Z feed rate, and the Z feed rate is not available here because we're threading. It knows how many threads it's going to count per inch, so it knows how fast it has to go down. You can't change that. That's what it's going to. And here it says Z clear is a half inch. What's that half inch? So somehow they're starting out with this. Well, -2 to -3. Okay, and Z clear is above -2, so we're starting up there. Some weird thing, some reason to go on. Anyway, that's the interface for threading. And this is the other part. When you get all these parameters in right, there, you just enter it in, you give it a name, and you say post. Post the file. So it will go through that and write the G code and do that. This part down below here, this whole thing, is actually the running. It's what you see when it's running. So here's the slider I talked about. What's that? Max level. The max level shows everything. Pretty sure. So you can start. So you move this over if you're not sure. Start it slow. Listen to the machine. See how it's cutting. Make sure there are chips coming out. You're not breaking anything. Then you can slowly speed it up. Here's if you want to adjust the speed rate or the speed on the fly. You can change it if it's not turning fast enough. Or you can change the feed rate on the fly if it's running. There is an emergency stop on there, but you can also hit stop here and let it stop. You can hit the space bar on the keyboard, that'll stop. And because this is Linux, when you hit it, it stops. It doesn't wait for some other decisions. So this also has a, you probably didn't notice, has a single step code. So what it'll do is, instead of just going all the way through your code, it'll do one line at a time. It'll run that line and then it'll stop. So in case you want to check something and see, or if you have a problem area in your code, you can start anywhere in your code, right click and say start here, and it'll start there. You can single step through them to see, okay, you saw it did that, and then it did that, oh, and then it did that. Shouldn't have done that, that was a mistake. So you can single step through. These are the positions of the, we don't have an A, so that's a fourth axis. We have them, but we've never hooked it up. So this is the X, Y, and Z positions, the literal positions. This line over here is when you turn the machine on, you have to connect the computer to the mechanical machine. So when you turn them both on, one light comes on, and reset flashes.
Yeah, oh my god.
So this is the wrong screen. But reset will flash. So you have to click that, and it'll talk to the machine. Both lights will come on. Now we're talking. And the first thing you do after you're talking, computer to the machine, is the computer needs to know where the head is. So it doesn't know where it is. So it makes you reference C, Y, and X. That means run the head up until it hits the switch, stop, and then come off a little bit. Run the table all the way to the right until it hits the switch and stop. That's the X, and then run the table all the way back or forward, I forget. Runs it all the way back or forward and stops. So it's hitting those 3 limit switches and now knows, okay, I know where the head is. Now we're ready to go. Now run your program, use your own origin, set the tape, set the head where it needs to be to start the program.
So you said that you were talking about that it's right below stop. So when you turn on the CNC, you'll see that flashing and you click that, and once you do that, then you can reference all your axes.
Yeah. And then once you reference your axis, what that does is it references the machine origin. Now you're going to set up your work origin, which you did in the CAM. I want to start in the upper left-hand corner. So you actually move the table, get that, bring that head down, put it right where you want to start it. You know, right on that surface in that corner. And then you hit 0x, 0y, 0z. And now it knows, okay, I know where I am. I'm right mind about me. I've got the head in the starting position. Now I'm ready to run the program. So that's kind of an introduction to this whole part. This is things that happen when you're running. Very important to get the right tool in. The tool will be in the program. If this number does not match the number in the program, it'll stop and say, put the right tool in, dummy. And it assumes that when you change that number, that you have put the right tool in. If you change the number but not the tool, it's going to break. All right, keep going along. You have the head full of stuff, lots of stuff. So, all right, you can take a break for 6 minutes.
Yay!
Can you just show?
Oh, I see. I found it as soon as you told me. Now it seems like you told me.
I told you how to
I
do
just
it.
got smart. Oh, did you get my plate? Thank you.
You take this one too.
Where's Roman's from? Did you see my picture of him?
I don't think you were here today.
Yeah. Oh, here he is. Roman. Oh, I just opened it. Where was it?
What are you doing?
Wait, who?
I just you're like, what?
Are we just gonna put our notes right here?
And then we get a picture close up to this stuff.
Alright, let's see how this can get done. My ride is gonna leave soon.
Well, is that going out?
Yeah.
There you go. Got it.
We've got some money now, so we can
Comes to your